The binomial theorem is going to give us a way of expanding binomials to any power. Now, we already know how to do this. A plus b to the 0 power is 1, because anything to the 0 power is 1. And a plus b to the first power is just a plus b, because raising anything to the first power doesn't do anything to it. But a plus b squared, which is a plus b times a plus b, is going to be a squared plus 2ab plus b squared. And then if we were to multiply that product by another a plus b, we would get a plus b to the third power, which would be a to the third, plus 3a squared b, plus 3ab squared, plus b to the third. And then if I were to multiply that product by one more a plus b, I would get a plus b to the fourth, which would be a to the fourth, plus 4a to the third b, plus 6 a to the second b to the second, plus 4 ab to the third, plus b to the fourth. And a pattern of the coefficients begins to emerge when I start looking at larger and larger binomial powers. And the pattern that emerges is something called Pascal's triangle. According to the textbook, Pascal wasn't actually the original person to discover this pattern in binomial expansion. However, he's noted with it because he wrote it down. And so the way that it works is anything raised to the 0 power is a 1. Anything raised to the first, a binomial to the first power, I should say, the coefficients are 1 and 1. A binomial raised to the second power is going to give you 1, 2, 1. A binomial to the third power is going to give you 1, 3, 3, 1. A binomial to the fourth power, 1, 4, 6, 4, 1. And what's really happening here is notice that all the outside of the triangle are 1s. To get the numbers that go in the middle, we do these adding, like 1 plus 1 is 2, or 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. So to get the next row, it would be 1, 5, 10, 10, 5, and then 1. The next row would be 1, 6, 15, 20, 15, 6, 1. And then you can continue it from there. Another pattern that emerged from this binomial expansion was what happened to the a's and b's. Look at the exponents. When we start looking at, let's look at the second power. When we started with the second power, I want you to notice that we started with an a squared, and then an a to the first, and then no a at all. And then the b's, we start with no b's, a b to the first, and then a b to the second. If you go and look at the binomial expansion to the third power, we have a to the third, a to the second, a to the first, no a. And then we have no b, a b to the first, b to the second, b to the third. So while the first term is decreasing in exponential value, the second term is increasing. So there are patterns that emerge by using the Pascal's triangle to do this thing called binomial expansion. So let's talk about an example. How do we expand a plus b to the 7th power? Well, it'd be really nice if we knew the 7th row of Pascal's triangle. So let's go back to Pascal's triangle here, where the 7th row is going to be 1, 7, 21, 35, 35, 21, 7, and 1. These are going to be all the coefficients of each of the terms in the expansion. There will be 1, 2, 3, 4, 5, 6, 7, 8 terms in the expansion. So this is how it's going to work. The first one's going to be 1a to the 7th, plus the next term is going to be 7a to the 6th, b to the first, plus the next term was 21, a to the 5th, b to the second. The next term is going to be 35, a to the 4th, b to the 3rd. And the next term is going to be 35, a to the 3rd, b to the 4th, plus 21 a to the second b to the fifth, plus 7 a b to the sixth, plus 1 b to the seventh. And that would be the expansion of a plus b to the seventh. Now they do get a little more complex, so let's look at this one. Let's use Pascal's triangle to help us expand 2 minus 3x to the fifth. Now the coefficients in the fifth row of Pascal's triangle are 1, 5, 10, 10, 5, 1. So the first term is going to be 1 times 2 to the fifth. The next term is going to be 5 times 2 to the fourth, negative 3x to the first. So instead of a and b, we have 2 and negative 3x. The next term is going to be 10, 2 to the third, negative 3x to the second. Plus, the next term will be 10, 2 to the second, negative 3x to the third. Plus 5, 2 to the first, negative 3x to the fourth. Plus 1, negative 3x to the fifth. Now in this one we actually have to do a little bit more simplifying before we're actually just done. So now I'm going to go back and I'm going to simplify. 1 times 2 to the fifth, let's see, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Plus 5 times 2 to the fourth times negative 3, let's see, is going to be, 2 times 2 is 4, times 2 is 8, times 2 is 16, and 16 times 5 is 80, and 80 times 3 is 240, but it's times negative 3, so it's going to be negative 240x. The next one, 10 times 2 to the third times negative 3 squared. Well, remember when you raise a negative to an odd power, the number stays negative. When you raise a negative number to an even power, it becomes positive. So what's going to happen in this binomial expansion is each term is going to have an alternating sign. So the first term is positive, the second one's negative. So the third one's going to be positive. So 10 times 2 to the third is 10 times 8, which is 80, and 80 times negative 3 squared is 9. 80 times 9 is 720, so plus 720x to the second. The next term is going to be negative. 10 times 2 squared is going to be 40, and 40 times negative 3 cubed is negative 27, is going to be 1080 x to the third. I should say this is what I just did. Now let's do this one. 5 times 2 is 10, and negative 3 to the fourth power is 81, so 81 times 10 is positive 810 x to the fourth. And then the last one is going to be negative 3 to the fifth power, which is going to be negative 243 x to the fifth. All the binomial, or all the coefficients in the binomial expansion can be found using a formula that we learned back in Algebra 2 called a combination. And the textbook uses a little bit different notation, but I'm going to go back to the one we used in Algebra 2 when we talked about a combination last year, because combinations usually end up on the ACT. Now we found out that there's a way of doing this on our calculator, but it actually has a formula to go along with it. And here's the formula. Now, what are those exclamation points? Those are known as factorials. Factorial is pretty easy. If I said, what is 4 factorial, I would be asking you, what is 4 times 3 times 2 times 1? That's all I'm asking you for. Now, in this formula, n is going to represent the power of the binomial expansion. So if you look back at the previous example, I was raising that previous example to the fifth power, so n would be 5. R would represent the term that you're looking for. So if I said I'm looking for the first term, R would be 1. If I'm looking for the second term, R would be 2. Depends on which term you're looking for. I shouldn't say that. R is going to be the term you're looking for minus 1. So in, let's talk about the third row of Pascal's triangle, where these were the coefficients. You could get the first coefficient by doing 3 and then 0, because the first term, r minus 1, would be 0. And then the second coefficient you would get by using 3 for n and 1 for r. And the next term you would use 3 and then 2, and the last one would be 3 and then 3. Now, combination on your calculator is found under Math. And then if you arrow over to PRB, it's number 3. And the way that you would type these in, for example, if I was going to type this in to find out what the coefficient is, first you would have to type in the 3. Oh, by the way, this is the notation the book uses rather than this, but that's okay. We'll get used to it. Then you would go to Math PRB so that this pops up on your calculator, and then you would type in the 1 and then enter. And when you hit enter, it'll tell you 3, that's the coefficient. Now, why would you use that to find a coefficient of something that's already in the triangle? You wouldn't. But if I wanted you to find the fourth term in the expansion of a binomial to the 20th power, you're not writing out 20 rows of Pascal's triangle. So that's where the combination is going to come in handy in a few minutes. Now let's practice with our calculator finding this thing called a combination. This would represent raising a binomial to the 9th power and asking you to find the 5th term. Remember that r is the term you're looking for minus 1. So if you go put that in your calculator, you should type in 9 NCR4. When you do that, it should tell you the answer is 126. In B, this would represent the power of 100 in the binomial, and you're finding the 4th term. So you do 100 NCR3, and the answer should give you 161,700. This, in part C, it would be, again, raising a binomial to the 100th power and finding the 98th term. So you would do 100 NCR 97. When you type that in your calculator, you get 161,700. That's kind of interesting. Why did these two end up with the same answer? Well, think about how the Pascal's triangle works. The values start at 1, and then they increase, and then they start to decrease, but you see repeating coefficients. So if you think about this, this makes sense, doesn't it? This would be the 4th term in, and this would be the 4th term from the end. And that's why they got the same coefficient. Let's talk about how to use this combination to find a particular term of a binomial expansion. Sometimes we don't want to do the entire expansion. We just want to find one particular term. So let's find the term that contains x to the 5th in the expansion of 2x plus y to the 20th. X to the 5th would be the 16th term into this expansion, because remember, the first term in the expansion is going to be 2x to the 20th power. So the first thing we want to do is we want to find, let me use a different color, we want to find the binomial, or the coefficient of that term. To find the coefficient, n is what you're raising the binomial to, which is 20, and r would be the term you're looking for, minus 1. Well, I said it's the 16th term in. I counted that using my fingers. So this would be 16 minus 1, which is the 15th term, which is also easy to get by just doing n minus r. So this is just n, and then n minus r. Now, when we do this in our calculator, 20 NCR 15, we're going to find out that the coefficient is 15,504. Now, for the rest of it, the first term in the expansion, the 2x, is going to be raised to the r power. Well, r is... Yeah, well, this isn't r here. You could have also found this, instead of doing 16 minus 1, you could do 20 minus 5. R is actually 5 in this case. And the second term, the y, is going to be raised to the n minus r power, which we said was 15. So in order to finish this problem off, we're going to have to multiply 15,504 times 2 to the 5th, and 2 to the 5th is 32. So you're going to find out that it's 496,128 x to the 5th, y to the 15th, which is much nicer than doing the entire expansion of this to the 20th power. In this last one, we want to find the coefficient of the term that has x to the 8th in it in the expansion of x squared plus 1 over x to the 10th power. Now this one is not as simple as the previous example, where you can just find the coefficient by doing 10 and then 10 minus 8. The reason is because both terms in the expansion have x's. So if you think about how this is going to work, the first term is going to be 1 x squared to the 10th power. The second term is going to be 10 x squared to the 9th power, 1 over x to the first. Well, that second term, if you were to simplify it, is going to be the term that has x to the 17th in it. So we're going to have to figure out where the heck the term with the x to the 8th is going to be. So this is how it's going to work. Let me get rid of all this for a moment. All right. So we know that n is 10 because we're raising this binomial to the 10th power. What we don't know is r. But we know that the bottom of this combination is going to be 10 minus r. And we know that the x squared is going to be raised to the r power. And we know that the 1 over x is going to be raised to the n minus r power, which in this case is 10 minus r. Let's do some simplifying here. Nothing's going to happen to my 10 minus r. But when I simplify, the exponential power rules tell me that this is going to be x to the 2r, and that this is going to be x to the negative first, and then 10 minus r. Because 1 over x is the same as x to the negative first. Okay, let's simplify that again. This is going to be x to the 2r. This is now going to be x to the negative 10 plus r. I'm going to make that r minus 10. Hey, these both have x's. The powers of exponents, or the properties of exponents, tell me that I can add the exponents. So 2r plus r minus 10 is going to tell me that I'm going to have x to the 3r minus 10. Now, remember I said I want the term that has an x to the 8th. So I want 3r minus 10 to equal 8. Well, I'm going to find out that r must be 6. Now I can finish this problem off. I want 10 minus 6. So we're going to do that combination in our calculator because all we care about is the coefficient in this problem. We don't care about the entire term. So 10 and then NCR, and then 4 is going to tell me that the coefficient of the term that has the x to the 8th is 210.